Okay, so the announcements are, I already posted the grades for your take-home quiz that you gave to me Wednesday night. Congratulations, most of you did great. There are some discrepancies. Some of you have some notation issues and some other things going on, happening, that I hope that you got that need to be corrected. So if you're confused or you have concerns or questions about how you need to do that, please, I'd be happy to help you out in my office time, which is going to happen between noon and 2 today. So come to my office hours and we can chat. Or I could put you in a breakout room with one of my tutors who'd be happy to also help you out. Some issues that I want to talk about. Quiz 0, and there's 2 quiz 0s in my math lab, my lab math. My math lab, whatever. You don't have, these 2 review quizzes are the only 2 quizzes that I will not ask you to upload any corresponding handwritten work for. So whatever score you get in my math lab is the score you're going to get. Now I understand that my math lab can be pretty grouchy about the way it wants the answer. And so you have to figure out how to make my math lab happy. And that's why I have you doing a pre-test with the learning aids turned on. So that's your job. So please don't email me and go, blah, blah. I mean, you can, and we can go over it, but more often than not, my math lab is correct and something went awry there, okay? So speaking of the uploaded work, which you are going to give me because quiz 1 is this Sunday, quiz 1, I'm giving you a 24-hour window to complete. Like I'm opening up the possibility for you to start it like at 8:30 in the morning Sunday, and then you have to upload it by right before class on Monday morning. But the actual quiz itself is only 90 minutes long, so you have to do it in one sitting, and there's something like 15 problems on it or something like that. And it's everything that we've done this week, and that's your job. And so I am going to let you have 2 attempts on this quiz, but for the rest of the semester, you only get 1. This is to test your fluency. I'm testing whether or not you know how to do things in your sleep, not, oh, let me go talk to my buddy and see how she or he does it. That's not what these quizzes are about. They're about you doing it on your own. And so I had one student, not this class, he was saying, oh, I'm really good at, you know, doing well on exams with a practice test. Well, yeah, of course we are. Now, that's why I gave you the pre-test for quiz 0, because I really want to ensure that everybody does the review. But for the rest of the semester, there's not going to be any more pre-tests, practice tests, or anything like that. So how could you help yourself doing a pre-test? You're going to do all your homework, all of it. The ones that correspond to that quiz. Why? Because all I do is I pick homework problems and different ones and throw them into that quiz. So if you have done all your homework and kept good notes, you'll do fine on the quizzes, provided you know what you're doing. Okay? So some of you didn't name your uploaded work appropriately. Like, for example, if I had done the quiz 0 the other day, I would have named my quiz Mimi Rasky quiz 0.pdf. Some of you didn't even name it. You had all kinds of weird names. I didn't dock anybody points yet, but you didn't follow directions. So in the future, I will dock you. Please name it appropriately, because when me and my grader are grading and we have to grade, you know, tons and tons of quizzes, and yours is named just some generic name like quiz or something. Not helpful. The order matters also. Please do the problems in the order that it's supposed to do. Don't like put a page that has problems 1 and 2 on it, and then the next page has problems 8 and 9, and then goes back to something else. I don't want to be scrolling all over the place trying to figure out where your problems are. So like it says in the instructions and on my syllabus, if it's out of order, the way you took photos of it and uploaded it, you're going to lose 2-letter grades. No graph paper, please. I can't read it. And you have to give me a single file. I've had students in the past where they take separate photos for each page and upload separate pages. I'm not going to even grade it. You'll just get a 0. I don't have time to download 5, 6, 7, 8, 9, 10 different pages and try to consolidate it on my end. That's your job. Consolidate it on your end. You have a free app. It will do it for you, okay? If you have any questions, come visit me in office hours about this, okay? So that's it for announcements. You have a quiz 2 quiz zeros that's due Saturday night, no uploading needed. That's in my math lab. Quiz 1 is going to be opening up on Sunday. That's your job. You will have to give me uploaded work by Monday morning and then right before class. Okay, so any questions? I'll check the chat. No questions? Okay, I'm going to do a file new. I want to talk about one of the problems on the quiz, because I had a lot of people who are doing it the way Briggs does it, and even though I didn't take off any points, I will in the future. I don't like it. So it has to do with integrating the derivative of arctan. So here's the rule. The arctan rule looks like this, and please take good notes, because for the future it is going to matter. I'm gonna dock you points if you don't do it this way. I know Briggs may have taught you the other way. I don't like it. It's very cumbersome and takes up too much time. The arctan rule basically says du all over a squared plus u squared is equal to 1 over a arctan of u over a, of course, plus c. Now, the way Briggs does it is Briggs teaches it like this. Dx all over 1 plus x squared is equal to, arctan x. And then, so if you have something else here, what they do like this is you've got this, they have you rewrite it where you factor out the a, and it's just, it's a nightmare. So you end up with the same thing, but I don't want to see it, okay? So let's just look at the problem that I gave you on your take-home quiz. You were supposed to split up problem 4 into 2 separate quotients. So I call it the split up trick. It's not really a trick, but my beginning algebra students think it is. So you were supposed to split it up into this integral plus the other integral. And I'm not going to do both of these, okay? I assume everybody in the room knows how to use the log rule, and most of you did great on this one. Using the log rule, 1 over u du's integral is ln of u. Fine. Okay, what about this? Well, here you were supposed to notice that 25 can be thought of as 5 squared, and 9x squared you can think of as 3x squared. And then if you use my little formula up here, the a is 5 and u is 3x. So write that down. So a is 5, u is 3x, and this 2 is just a multiple. You can pull that out. And du is 3 dx. So I need a 3 in the integral. So what I'm going to need to do here in order to continue this process is put a 3 in there, provided I divide 1 out. So now it looks like 2/3, 3 all over 5 squared plus the 3x squared. And now you can apply the arctan rule, where you've got the 2/3 is already there, this multiple, and then multiply that by 1 over a, 1 over 5, arctan u over a. So for us, that's 3x over 5, of course, plus c. And then this you should multiply together. That'll be a coefficient of 2/15. Okay? So if you have any further questions on this, I'm available in my office hours. But I want to see it done this way, because when you factor out, some of you would factor out the 25 and rewrite this as 25 plus 1 over 9/25 x squared. Good God, man. Pain in the butt. All right? So let me get out of here. And let's go to what we're supposed to do today. We've got a lot going on. Rectangular coordinate system. I'd like to get done with this fast, and I'd like to get into the dot product. So that's my plan today. And we're going to finish up part of the next section. Part of the, and don't worry, your quiz will only cover the portion of dot product that, that I cover. So we won't do that whole section, so don't worry. Okay? So last time we started the 3D coordinate system, and this is what the word space from now on is going to mean 3D. Just like the word plane meant 2D, the word space means 3D. So when we work in space, we have the rectangular coordinate system being one of many coordinate systems that you can do business with. And I already did this from last time where we broke it down and we noticed there's going to be 8 octants, and you've got 3 coordinate planes, the XY plane, the XZ plane, and the YZ plane. And now let's talk about denoting points. So when you're in this 3D rectangular coordinate system, and I did mention that the x-axis is pointing to the left, the y-axis to the right, and the z-axis straight up. If you're going to graph a single point, you're going to use an ordered triple instead of an ordered pair. So this is important for you to make the distinction. And so this point here, they plotted a point right there for you, 3, 4, 5. Cool. So you can see it's got parentheses. That's how you denote a point, with parentheses. And then the coordinates are delimited by commas. And there's a point down there in the XY plane. Notice in the XY plane here, when you're in the XY plane, the Z coordinate is 0. And then this is a x-intercept, 3, 0, 0. And you have the origin, 0, 0, 0. Okay? So let's look at some key formulas, and all this stuff's going to be on the quiz, which is opening up for you on Sunday, all of it. So the distance formula, let's do a quickie review. What is the distance formula in 2D? So, let's say here we have 2D, the XY, the rectangular coordinate system. Let's say you had a point P down here and a point Q way the hell over there. And you're like, what's the distance between those two puppies? Well, if you have the coordinates of P, let's say x1, y1, and let's say the coordinates of Q are x2, y2, the distance D, and hopefully you saw this in an algebra class, is the square root of the sum of the squares of the differences of the coordinates. And that's actually the Pythagorean theorem happening there. So what is the distance formula in 3D? So if you have 2 points in space and there are the coordinates, you're just going to extend this distance formula. So you're still going to have a big old square root, and you're going to have the sum of the squares of the differences of all 3 of the coordinates, x's, y's, and z's, like so. Okay, that's it. It's pretty easy. Now let's talk about the midpoint formula. So you probably saw a midpoint formula back when you did 2D. So a quick review, in 2D, like if somebody said, hey, I want the midpoint right here in 2D, I'll call it M, the midway point between P and Q in 2 dimensions, that M has coordinates, and here's how I like to think of it. Since it's midway through, I like to think of averages. Like, you guys know how to take the average of 2 test scores? You add them up and divide by 2, right? So the coordinates, the x coordinate for M is just the average of the x coordinates for P and Q, and similarly the y coordinate is just the average of the y coordinates. So for us in 3D, if you think again of just averages, you'll get an x coordinate that's just the average of the x coordinates of P and Q, a y coordinate that's the average, and a z coordinate that's the average. So think average when you're doing a midpoint. Okay, fine. And then finally, let's do the standard equation for a sphere. So before I do the standard equation for a sphere, let's do a quick review. What's the standard equation for a circle in 2D? And you should have learned this in some algebra, or maybe even you saw it in your pre-calc course, hopefully. So if you have a circle where the center here is, I'll just say AB, and you have some circle like this, and you know the radius is R, then you hopefully saw that x minus a, the quantity squared, plus y minus b, the quantity squared, is equal to r squared, was the standard equation for a circle. What about a sphere? Well, a sphere is sort of the 3D analog for a circle, essentially. It's a 3D solid. And so if you have a sphere, let's see if I could draw one, here's a sphere, like so, and you have the center point ABC and the radius is R, it starts out similar to the circle equation, but it's got one more term there on the left-hand side. So the difference z minus the z coordinate of the center point, the quantity squared. So that's equal to r squared, and there's your standard equation for a sphere. So let's do a couple of problems that involve what we just learned with these three formulas, and then we'll do what I call the grand finale for this, where all three formulas get involved. And these kinds of problems will be on the quiz, so please, if you're half asleep, it's Friday, it's been a long week for all of us. I'm dead. I'm sure you're dead too, and you've already made up your mind that maybe it's time to quit.
No, not yet.
Not yet, not yet. Hold off, okay? So you probably saw a problem like this in pre-calc, except they did it for a circle, not a sphere. So here is a big old equation that looks pretty hellacious, and they want you to get the equation into standard form. So if we can get it to look like this, that'll be awesome, because then we'll easily be able to cherry pick the coordinates of the center point and cherry pick off the radius quickly. So that's the point, to help us get the center point and the radius. So what I'm going to do, folks, is I'm going to rearrange this equation, and then I'm going to complete the square 3 times. Okay, so here we go. I'm going to put the x terms next to each other, so I have x squared and 9x, and then leave a little bit of room before you start writing some more terms. Let's put the y terms next to each other, and then leave a little bit of room. And then let's put the z terms next to each other, leave a little bit of room. And then the constant, move it to the other side of the equation by subtracting it from both sides of the equation. So when I subtract 19 from both sides, I get negative 19. So here we have a big mess. Now what's the point of me doing all this? Because I'm getting myself ready to complete the square 3 times. I'm going to add a mystery number m1 to this polynomial here that's going to actually make a perfect square. And I'm going to add another mystery number, I'll call it m2, so I'll get a perfect square there. Perfect square trinomial, they call it. And then I'm going to add another mystery number, I'll call it m3, to these guys here to get another perfect square. Now, you can't just add things to one side of the equation and get away with it. That's not legal. So all of 3 of these mystery numbers, I better also add them to the right-hand side so everything evens out. Now, what are these mystery numbers? Well, in algebra, when I teach algebra, I always teach my students that the trick formula to figure out your mystery number is b over 2 squared, where b is the middle coefficient, the coefficient of the x to the 1 power term. So for us, the m1 is going to be 9/2 squared, which is not pretty, but whatever. So that'll be 81/4. I know, that's pretty gross. And then m2, so this mystery number, is going to be negative 2 over 2, the quantity squared. But good news, that's just negative 1 squared, which is 1. That's not too bad. And then the third mystery number will be 10 over 2 squared, but that's just 5 squared, which is 25. So when I do all this, adding these mystery numbers here, don't forget to add it to the other side. Also, what you're going to have here is x squared plus 9x plus 81/4. Believe it or not, that factors as something squared. So what? It's going to be x, in this case, plus, does anybody know?
Nine over 2.
Good. 9 over 2. Perfect. Plus, and then this is now a perfect trinomial, perfect square, because we got that going on. How does that factor? That one's probably pretty easy, right?
X minus 1 squared.
You're almost there, except for the variable. Instead of x, it's
Y, yeah.
Yeah, bingo. And then these guys, z squared plus 10z plus 25, perfect square trinomial. What do we get?
Z plus 5 squared.
That's right. Z plus 5. And then the right-hand side, you want to whip out a calculator of some sort and add up everything. And it's not going to be pretty. I'll just tell you right now, it's 109/4. I know, pretty disgusting. Now, good news. This is an equation for a sphere in standard form. Standard form. So it's going to be super easy to pick off your center and your radius. Okay, help me out here, folks. What is the center point? It is going to be an ordered
It'd be-
triple because we're denoting a point. So what is the x-coordinate of the center point?
Be negative 9/2 for the
Good,
x.
negative. And yes, negative matters because if you look at the standard equation for the sphere, it's x minus something, and that something has to be next to a minus. So how about the y-coordinate?
1.
Z-coordinate?
-5.
Beautiful. Okay, now the radius, you know that this thing is r squared, right? So r is going to be the square root of 109/4, which I'm going to use the law of radicals. Radical of a quotient is quotient of radicals, and I'll just leave the square root of 109 because that's not more, you can't simplify it any further. And so the radius is square root of 109 divided by 2. And we're done. So that's easy peasy. You'll have some homeworks like that. And that's fair game for a quiz. Now let's do one of my most favorite of all time problems. And you may want to make a note to yourself. This for sure is going to be on midterm 1. I'll change the numbers, of course, but this is like one of my near and dear to my heart problems. So if you're paying attention, on the midterm. So if I were to draw a picture of this, you know, you've got the point, you know, 5, -2, 3. I'll just say it's like right there, roughly. And then another endpoint of a diameter, 0, 4, -3, which looks as probably somewhere down here. And if I were to draw a sphere with those guys as endpoints of a diameter, well, I'm not very good at drawing in 3D, but you have some sort of ball here, if you will. So there's my sphere. So I hope you can tell that these 2 points between them, that would be the diameter of the sphere. The distance between those gives me a diameter. Now, there's a few ways to do this problem, different approaches, and so I'm going to do one approach that will work for me. But I claim that I'm going to need all 3 formulas from the last page. I'm going to need the distance formula, the midpoint formula, and the standard equation for a sphere formula. So they'll all come into this. This is why I love this, and it will definitely be on your midterm. So first up, I'm going to find the distance between these 2 points, because that's going to give me the diameter. And then if I just take half of that, I'll get the radius. Why? Because radius is always equal to half of a diameter. So the diameter is going to be a distance formula type of problem. And so using the distance formula between these 2 points, I'm going to take the difference of the x coordinates, and it doesn't matter what order because we're squaring. And the difference between -2 and 4, so -2 minus 4 squared plus 3 minus a -3 squared. Be careful, there's a lot of negatives flying around here. So I have 5 squared plus -6 squared, plus 3 minus a -3 is 6. So this is square root of 25 plus 36 plus 36, square root of 97. Now keep in mind that's the diameter. So the radius is really half that. So let's save this for later and keep going. So I claim that the midpoint right here, midway between these 2 endpoints of a diameter, is the center point. So to get the center point, I'm going to use the midpoint formula from the previous page. Cool. And remember, the midpoint formula is just about finding averages. So the center point, when I find the average of the x coordinates of these 2 points, I'm going to go 5 plus 0 divided by 2, and then take the average of the y coordinates, -2 plus 4 divided by 2, and then take the average of the z coordinates, 3 plus -3 divided by 2, and then use a little bit of arithmetic to simplify. 5/2, this middle coordinate is what? 2 divided by 2, which reduces to 1, and then 3 plus -3 is 0. 0 over 2 is 0. So 5/2, 1, 0 are the coordinates of my center point. Awesome sauce. And now your final answer, here it is, people. X minus 5/2, the quantity squared. And please don't use decimals in my class. Like, in other words, I prefer 5/2, not 2.5. Sometimes it's okay to use decimals, and watch, my math lab will tell you a lot of times if it wants decimals or not. A little more forgiving maybe. y minus 1, the quantity squared, plus z minus 0, that's just z squared, is equal to the square root of 97/2 squared, which this thing over here is really just 97/4. Okay, I'm done with that problem. Let's pause for a moment and I will take questions.
So was that a standard form of the sphere we just found?
Yes, right here, with the 97/4 here, that is the standard equation for a sphere.
Okay.
That's the guy.
Will the online notes of this be available today? Because I want to
No,
go.
I don't post any of my notes anymore until the weekend before the midterm.
What about lecture?
I do post the recorded lecture. So my invitation to you would be when I post the recording, you can rewatch it and then stop it or rewind it or what have you. Okay?
No, that's what I want to do, because the first time over, I always know from previous experience, you go a little fast for me.
I know.
And
I got cover stuff. So that's why I post the recordings, and you're welcome to watch them.
Definitely. That's.
Now, there's a reason behind me kind of being a little bit reluctant here to do notes. I want to make it a little more difficult for people to not come to my lectures and act like they're here and zone out and think, well, I'll just get the written notes and not really have to focus and concentrate and do the notes themselves. That's kind of my goal here. And if you took your About the Syllabus quiz and you read the corresponding article about taking notes with pen and paper is more beneficial to you, that's, because of the desirable difficulty of making things stick, that's my goal for you. I want it to make it a little bit more difficult because that's desirable difficulty for you. You'll get it better rather than just somebody handing you everything, okay?
I just want to fit all the notes in one page, more so.
Yeah, well, it gets hard. I try to make enough room, but, Okay, so now let's talk about vectors in space. So good news, you already know about vectors in the plane. And so a lot of what it has to do with vectors in the plane, which we did earlier this week, which even the notation and so on, is still true for vectors in 3D. Of course, we have to extend it to make room for the third axis there, the z-axis. So remember that one of the ways to denote a vector is using component form. So component form involves angular brackets, and the scalar components, which are just pure numbers, are delimited by commas. There's the second way is where you get the I, J, K in here. Well, when we did it in the plane, we just had I and J only, but I'm going to introduce a brand new standard unit vector called K. So I is a little different than the I from the plane because the I vector now has 3 components in it because this is the I that lives in the 3-dimensional space here. And then J has a third component, so his components are 0, 1, 0, and K's components are 0, 0, 1. So if you look on a picture here, if you go to the next page real quick, here's a little picture of the I vector. He's right there pointing in the positive X direction. J is this green vector pointing in the positive Y direction, and K is pointing straight up in the positive Z direction. So why do you care about I, J, and K? Because the third way for the format to denote a vector is the standard way that our physics people like to use, the linear combo of the standard unit vectors. Some number times I hat plus another number J hat plus another number K hat. So that's rule number 2 here. Number 3, if you have 2 points in space and you want to create a vector that is between them, and let's say the vector is PQ, the PQ vector here, which is they're denoting V, you want to do terminal minus initial for the X coordinates, terminal minus initial of the Y coordinates, and then the last component is the difference of the Z coordinates. Similar to 2D, you're just extending it one more. Equality of vectors, same kind of thing. If one vector is equal to another vector, if this vector U equals V, which means they have the same direction and the same magnitude, to quickly check if they're equal, you just check to see if their components, each and every single component matches. So this U had one better match the U2, excuse me, U1 matches V1, U2 matches V2, and U3 had better be the same number as V3, and then everybody's happy and they're really equal. If even one of them isn't equal, those vectors are not equal. Vector addition, similar to 2D, you're going to create a brand new vector here. And so the brand new vector will have the sum of the x components as his x component. You'll take the sum of the y components to get the new y component, the resultant. And lastly, you'll take the sum of the z components to get the z component. Now, if I ask you to rewrite this in the IJK format, which I could, then it would look like this. Whatever this number is, U1 plus V1, you'll multiply it by the standard unit vector I hat plus this number times J hat plus this other number, whatever that ends up being, times K hat. That's all. Unitizing a vector, same type of process as before. You can stretch or shrink your vector in order to make it unitized so it only has a magnitude of 1, and the unit vector pointing in the same direction as the original vector as before is the vector divided by a scalar, where the scalar is the magnitude. And the magnitude is found the very same way. Did I mention that here? Let me just do a side note here. So magnitude of a vector V, say with components V1, V2, and V3 is, I like to denote it with double bars. I know Briggs has single bars. That's where me and Briggs differ. That's just one way that me and Briggs differ. I differ on so much. And we started off the lecture with one way. I don't like the way Briggs presents the arctan rule. It's very unconventional. Other normal calculus books do it the way I showed you. So this would be a vector here, which would have V1 all over. I'm just going to put magnitude, comma, V2 over the magnitude, comma, V3 over the magnitude. In scalar multiplication, similar to the 2D, you just distribute your scalar over your vector and you end up with a stretched or shrunk vector. Okay, moving on. They're just giving you a picture of this. Let's do a problem here. So here they're giving you 2 points in space, and they want you to do the component form, and then do the same vector but rewrite it as a linear combo, and then finally, or almost finally, give the magnitude and then unitize it, and then do a unit vector pointing in the opposite direction. Okay, so I'm going to put you in breakout rooms, and you're going to do this with your breakout buddy, okay? So, wow, we only have 24 people in the room. I thought we had 31 in the class. That's not cool. I hope you guys, everybody here, I just want to say kudos to you for showing up on a Friday. Let's do 10 rooms. Okay, so I'm going to open all rooms, and you're going to go into your room with your buddies and go and try to do this problem together, okay? Bye.
I see we're the only ones that have left, so I'm guessing that either everyone is still working on the problem or mm,
Yeah, on Wednesday we also had a breakout room, but um, Miss Rasky was the one who ended it. Not like Monday where like some of us just came back. She just ended after a couple
that was
minutes.
Wednesday, right?
Yeah.
Where she ended it herself?
Yeah.
Oh, okay. Okay.
So she can end it and like bring us all back. I'm just guessing she's giving us time.
You know, the interesting thing, like when we left, this is not the actual, how would you call it? Like the actual meaning, because she's not here.
I think it is the actual meeting. She's just visiting the other breakout calls to see how people are doing.
Oh, yeah, yeah, you do have a point, Augustine. Man, and you're also tech savvy. So are you planning to become like a engineer or something like that?
Computer science.
Oh, computer scientist. Okay.
Yeah.
Cool. Yeah, computer scientists. There's a lot of like you'll never be out of a job basically if you're a
Yeah.
computer science major. Like a
There
lot
are
of a lot of
job
companies want
opportunities.
computer science majors. So do you know like do you know how to code or like do you code?
Yeah. Just the basics of Java. Nothing too advanced right now.
Also, you're learning JavaScript?
Yeah.
Oh, okay, cool. Yeah, it's a nice language.
Mhm.
I remember I was trying to learn a bit of Python.
Oh.
I was using this website called Code Academy. It's called,
Mhm.
and yeah, I like the way that website works because it's like it's nice to look at. You know, it's very user friendly.
Yeah.
That website, but there are many ways to learn how to
Yeah.
code. You got different like boot camps or college classes and whatever. A lot of different ways.
Yeah. After transferring, I'm probably gonna take a class or two for Python also, because it's the more commonly used language at the moment.
Oh, you're thinking about learning Python too?
Yeah.
That's cool. That's cool. Yeah, Python is a really useful language. It's used a lot. Like, well, Python is you could use it for a lot of things, but
Mhm.
I think it has especially applications in like data science they call it
Mhm.
or
Yeah.
data. So, yeah, there's a lot of stuff you can do with that language. Man, she's taking a while. I wonder if she's still in the breakout room.
Probably. She's just I don't know. People are probably having troubles with this. Oh.
Hey guys, can you hear me?
Hey, I can hear you.
Fantastic.
Yeah, we can hear you.
Okay. How'd it go here?
Got it.
Yeah? So I'm going to do this pretty fast. I'm
Good.
hoping that everybody got the same answers. So if you didn't or something's weird, stop me and go, what the heck? So AB, if you're forming the vector AB, that's the vector that's connecting these 2 points where the the tip is at the B, you're going to go 0 minus -2 for the x component, -4 minus 3. Remember, order matters, terminal minus initial, and then after doing a little bit of arithmetic here, you should get this vector in component form. Remember, component form has these angular brackets that I'm kind of enforcing here, and the numbers, the scalar components, that's what those numbers are called, are delimited by commas. You see these are commas in between? Nowhere do you see an I, a J, or a K when you're doing component form, okay? For letter B, all you had to do is look at your answer to letter A, easy peasy, take the first scalar component, multiply it by the standard unit vector I hat, and then -7 times j hat plus 3 times k hat, and we're done. There's no commas here. And there's no angular brackets. And yes, it matters. So if I see on your handwritten work, you're confusing one format with the other, even if my math lab says you're right, I'm going to take away a point or two for yucky notation, because that matters. Okay, magnitude. That's what they're asking for here for letter C. Magnitude. So the magnitude, if you've been following along, is simply the square root of the sum of the squares of the components. Now I know that this middle component is -7, but you know that I know that I know that you know that when you square a value, it's going to go positive. So I don't bother putting the negative just because I'm sort of acknowledging that point. Okay, so then what the heck is 4 plus 49 plus 9? I get 62. Now if this were a radical that could be simplified a little bit more, in other words, if 62 had a perfect square factor in there, I'd want you to go one extra step. Otherwise, I dock you a point. But 62 doesn't have any factors that are perfect squares, so you're done there. Unit vector. Remember, a unit vector, this is what I call unitizing, that's going to automatically point in the same direction, is your vector, which was 2, -7, 3, divided by this scalar, and then actually distribute the scalar over each of the components. And I'm doing component form. I didn't specify in this one, so I guess I would have given you full credit if you had written it like this instead. That's also legit. Now what about a unit vector pointing in the opposite direction? No problem. Just take the unit vector that you got from the previous problem, and all the components take the opposite in sign. And so this would be the unit vector pointing in the opposite direction. Okay, how'd we do? Questions?
I was just a little mixed up with the directions. So for B, there was the mention of 3 standard unit vectors, and then in D, it mentions a unit vector.
Yeah, when they just say a unit vector, they're not referring to the standard unit vectors.
So it's as simple as that?
It's as simple as that.
All right.
They're asking for a unit vector pointing in the same direction as V. That's telling you, I need to stretch or shrink, as the case may be, my original vector so that he's only 1 unit long in length. That's what they're asking. And that's a very special skill that you're going to need all the way up through the final, is unitizing a vector. Does that help?
It does. Thank you.
Okay, any other last minute questions? Because I'm moving on. Okay, now let's talk about parallel or not. So how do you know if 2 vectors are parallel or not? Well, you could look at a picture of them. You know, somebody had graphed them already and check to see if they're parallel. That's one way, but then you got to draw a lot of stuff in 2D and 3D, which is a pain. So pictorially speaking, I do want to say, like, if that's a vector U, then this vector V is obviously parallel, right? But what about if I'm pointing in the opposite direction? Isn't W parallel to V and also parallel to U? Yes.
Sure.
All 3 of these vectors are parallel. Okay, keep that in mind. So 2 non-zero vectors are parallel, and this is one way to check if vectors are parallel, is if one is a multiple of the other. That's it. If one vector is a multiple of the other, by default, they're parallel to each other. That's all you need to know. Now, does the scalar matter? No, but the scalar has to be, legit. So what I'm saying is, here's a vector W they're just handing you. And then they're giving you two other vectors, and they're going, hey, do these vectors, are they parallel to W or not? Sometimes you can tell quickly by eyeballing it, but other times it may not be apparent. So check out these two vectors. Does W look like it's a multiple of V or vice versa?
Yes.
It does, because do you see that if you multiply all three of these components by 2, 3 times 2
negative
gives
2.
you, excuse me, it should be -2, sorry. 3 times -2 gives you -6. -4 times -2 gives you +8. -1 times -2 would give you the 2. So yeah, they're multiples, so the answer is yes. Now, most of the times I'm never going to give you something that easy. So another way to check analytically would be to say, hey, does V look like it's a multiple of W? So that's one way. So if I'm saying that 3, -4, -1, and I don't know why my screen here is so, I don't know, Microsoft Surface, I'm not a big fan. If this is the same as that, and I'm going to distribute the scalar over here. So I have -6c, 8c, 2c. So you remember, if you have a quality of vectors, you have to, if the components match. So you need 3 to be the same as -6c. I would need -4 to be a match to 8c. And I would need the last components to match. -1 has to be equal to 2c. And then after solving for c 3 times, sorry, my handwriting is atrocious, especially on this Surface Pro because it's such a crappy computer. Are all 3 of these c's the exact same number after reducing, yes or no? Hello?
Yes.
I think
Yes.
so.
So that means parallel. If even one of them was different, then it wouldn't be parallel. So that's one way to check. So check out these guys. Are these guys parallel to each other? Yes or no?
No.
No, they're not. Oh, sorry. So the reason why is because -6 times -2 does give me 12. 8 times -2 does give me -16. It looks like the C that we're hoping for is -2, but 2 times -2 is supposed to be -4, but we have a +4 there. So that's not working. So these are not parallel to each other because one of the C's is different. I hope that's helpful. And yes, this kind of stuff is going to be on the quiz. It might even be harder than what I'm doing here. So heads up, do your homework before you do the quiz Sunday. Keep up with the homework. Like, even though I let you have a whole week to finish out on the homework, and that's cool, you can be procrastinating. The quizzes are testing your fluency, quickness of being able to do problems. So that's something that you want to keep in mind. Okay, now I'm going to show you by example 14 why I'm not a big fan of the IJK format that our physics brethren like. How would you write this vector in component form? Which means you're going to have brackets. Yeah?
4, 0, -5.
Very good, Yara. Good job. Fantastic. How did you know that there was supposed to be a 0 in the middle there, Yara?
Because there's no J.
Good. Bingo. Does everybody see that? So one of the reasons why I'm not a fan of the IJK, because sometimes if I'm in a hurry and my eyeballs aren't focusing up correctly, sometimes I look at that and I might not see that that's real, there's a J missing or whatever, and I might accidentally write it as 4, -5, 0. Or worse yet, I may accidentally think of that K as a J, and I might think that it's a 2D vector. But anytime you've got a K hat in the mix, that means by definition, it's going to be a 3D vector, not a 2D vector. I'll tell you another secret. What if I gave you a vector that was 4i hat minus 3j hat? Just say. And I said, hey, write that in component form. But I didn't tell you anything about the vector. You might go, oh, well, that looks like it's a two-dimensional vector because it's only got I and j going on. So I'm going to write the component form. Oh, man, my handwriting is 4, -3. And then I might go, aha, I didn't tell you this. It was a secret, but you blew it. I'm going to go, well, what do you mean? Well, this vector really is a 3D vector. So 3D vectors don't have the k-hat term. So if I had told you it was a 3D vector, then you would have gone, oh, okay, that means I need that third component. See, do you see that there can be some confusion if you use the IJ format, which is why I'm not a fan, although our physics brethren, that's their favorite. I get people who are like physics majors and they love the IJ stuff, and I'm like, yeah, knock yourself out, but I'm not a fan. Okay, that's just a little side note on why I hate IJK, but you still have to deal with it the rest of the semester. Okay, now I'm going to give you a going backwards problem. Suppose I gave you a vector and I gave you his initial point, but I didn't give you his terminal point. So here's the vector P, and then I'm just going to name the terminal point Q. So PQ is the same as the vector V. They're the one and the same. And I gave you the coordinates for the P, but I didn't give you the coordinates for Q, but I want them. Like, you give me. Well, how the heck do I do that? Well, the unknowns are the coordinates for the terminal points. I'm just going to give them names, X, Y, and Z. So what has to be true? Well, when you form the vector PQ and you go terminal minus initial, terminal minus initial, terminal minus initial, this has to be the same as the vector V. So it has to have components 7, -1, 3. Now you're going to use equality of vectors again. PQ had better be the same as V, so you equate the components. So X minus minus 2, which is really X plus 2, had better be equal to 7. Those have to match. The Y minus 3 has to match the -1. So I write those down. And the Z minus 5 has to match the 3. And now all you do is solve for X, Y, and Z, easy peasy. This is like a beginning algebra problem. X, after subtracting 2 from both sides, is 5. Y, after adding 3 to both sides, you get -1 plus 3, which is 2. And then here, if I add 5 to both sides, I get Z is 8. So the Q has coordinates 5, 2, and 8. And I'm done with this problem. So I was able to recoup my coordinates of my terminal point by my knowledge of creating a vector, knowing what the 2 points of the tip and the tail, essentially. Okay? Tail and tip. Questions?
No question.
Everybody's pretty quiet.
I got lost at example 13 with the parallel thing.
Which one did you get lost on?
On A, like how can you tell if it's equal?
I'm gonna
parallel. Sorry,
I
parallel.
don't know, Vanessa. The thing is that you're not sure.
Yeah.
You're asking a question. You're going, is this really? So I should maybe put a question mark here. Question mark. Or is one vector a multiple of the other? So
Okay.
it's really a question mark equality. Like, is it? And then in this case, it turned out to have equality because all of the C's ended up being the same guy. Does that help?
Yeah.
So I don't really know. Like, if I tried to do the same strategy for part B, which I didn't because I was trying to go fast, and I apologize for that, but I'll slow down a little bit. So if I was going to do example 13 part B, and here's my vector V and the vector W they gave me, and I'm saying, are these guys parallel or not? Parallel? Yes or no? So the question I want to answer is is one vector equal to a multiple of the other? So is V equal to a multiple, and I'll put question marks all over the place to make a point here, Vanessa, this is for you. Does that guy equal a multiple of the other guy? So does this vector V, question mark, equals some weird scalar times the W? And then please distribute your scalar over here. Vanessa, tell me if you're lost right now.
I'm following.
You're following, okay. Now I have equality, but it's sort of like, is it equality? Like, does this guy on the left really equal that guy on the right? I'm not sure. If they really are equal, I better be able to match their components. So 12 better be equal to negative 6c. This middle component, negative 6, had better be equal to 8c. And then the last component, 4, had better be equal to 2c. That all three better be true. Now, if I solve for c 3 times, am I doing this right? Oh, this is a 16. Sorry, I wrote this down wrong. Sorry. My bad. This was a 16. I copied it down wrong. Okay. So far, it looks like I'm going to say yes, but not so fast, because this last guy, when you solve for his c, I get positive 2. So this guy is sort of messing up the whole thing, and because he's
Okay, I got it now.
not parallel vectors. Does that help?
Mm-hmm. Thank you.
Cool. All right. Anybody else? That's a big hot mess. I feel sorry for somebody who didn't come to class today. When they do read these notes, they're going to go, what? That's why you want to come to class.
I had a quick question for 15.
Yeah. Which one?
So, for 15. When,
Yeah.
When you find the vector of PQ,
Mm-hmm.
and you put x minus.
Yeah, because this is, remember you have to do terminal minus initial?
Yeah. So.
X minus 2. Y minus 3. Z minus 5.
How do you get the x plus 2 equals 7?
Because PQ is the same vector as V, where V was given. That's understood. That's what they're telling you.
Oh,
In the problem, actually.
Yeah.
They're saying, hey guys, find the terminal point of this cool vector V, which they gave you, which has components 7, negative 1, and positive 3. And his initial point is P, but they're not telling you what the terminal point is. And I just said, well, let's name our terminal point Q. Let's give him a name at least. That's our unknown. And we don't know the coordinates of our terminal point. That's what the also unknown. In fact, that's what the whole problem wants you to give. And so I gave them names. I gave them variable names, X, Y, and Z, for the X, Y, and Z coordinates of this unknown terminal point. Now you got to go get them. Does that help?
Yeah, thank you.
So those components have to be equal. Okay, I'm going to move on. Let's do a force diagram in 3D. Try not to freak out. Let's say 3 forces act on each other. So 2 of your forces are at an angle of 100 degrees with each other, and they have magnitudes of 25 newtons and 12 newtons. Now, nobody is drawing a picture for me, so I'm the boss. I get to make the command decision. Let's start in 3D, or excuse me, 2D. So 3 forces act. 2 forces are at an angle of 100 degrees. Okay, one of them has a magnitude of 25 newtons. Let's make it this guy here. So there's 25. I'll make that first vector, even though they didn't say so. I'll call it F1. And by the way, newtons is a metric version of a force, okay? The English would use pounds. So in metric, they use newtons, which is denoted with a capital N for Nancy, newtons. So his magnitude is 25. That's why I know this little point right here is sitting at the 25 on the x-axis. So F1, because I decided to have him be at 0 degrees, his component form would be 25, 0. Now the other vector is making an angle of about of 100 degrees, so let's say he's over here, and he's not as long because he only has a 12 Newton magnitude. Let's call him F2. Now F2, now I'm going to use one of the formulas I gave you guys the other day. It's magnitude times cos of the angle for the x component, like that, and then magnitude times sine of the angle for the second component. Now they're telling me a third force is perpendicular to these two forces. So this is where you're going to have to kind of go with me now. I'm going to make this go on the XY coordinate plane, and then I'm going to have to work in 3D now. So if you guys can follow me here, and yes, it means you're going to have to kind of follow in 3D. The F1 is on the positive x-axis. There's my F1. And then I'm making a 100-degree angle here in the XY plane is F2. And if F3 is going to be perpendicular to both of these guys, F3 is going to be pointing directly vertically upward in the positive z-axis direction. I'll call him F3. And his magnitude is 4. Now, because he's pointing directly vertically, this tip of his little arrow there has coordinates 4, 0, 0, which means his component form is also 4, 0, 0. And now that I'm working in 3D, I better give each of these other vectors a third component, which automatically will be 0 because they lie in the XY plane. Now, the question they're asking is, calculate the magnitude of a force that would be able to counterbalance all of these forces. Well, that's a fancy schmancy way of saying, add up all of these forces together and figure out what the overall magnitude is. That they didn't actually say that, but that's all they want you to do. So this is what they want us to find. They want us to find this magnitude. That's all. Go get it. That's all they're asking. So what you're going to do first is you're going to go get F1 plus F2 plus F3. So your F1 plus F2 plus F3 is going to be a big old vector, and you're just going to add all the x components together. By the way, I screwed up here. Nobody said anything. I screwed up big time. This guy has actually 0, 0, 4. I don't know what I was thinking when I was doing 4, 0, 0, because he's pointing directly up there. My apologies. That's 0, 0, 4. He's got a z component, but no x and y components. So when you add all the x components together, you got the 25 plus this weird number, 12 cos of 100, good God, what that is, plus 0, and then you add all the y components together. Okay, that's going to be 0 plus 12 sine of 100 plus 0, and then you add all the z components together like this, and then you'll get a weird vector, and then you're simply going to take the square root of the sum of the squares of all of the components, and then use your calculator in degrees mode, because it's going to be some funky number, and I get approximately 26.092 N for newtons. And that's the final answer. Okay, we're officially done now with, I think, 13.2 or whatever, okay? So now I need to do dot product in the next half hour. So I'm going to bomb out of this file. I got to call up a new file. So we're now going to start 13.3. Congratulations. Oh boy. So I'm not going to finish 13.3 today. So I'm going to do a little piece of it, just knowing about dot product and finding the angle between two vectors. Just that piece of it is all you need to care about. And that piece of it will be on the quiz Sunday. Well, what about the rest of it? Are we not responsible? No, you're going to be responsible. Don't worry. What's going to happen is the following quiz, the following week, I'll pick up the last half. of section 13.3. Okay, so it's just a good marker point to end. So for those of you who have already taken a physics class or Math 254, you may already be familiar with dot product. And if all I can say to that is awesome. So you have a little bit of feeling for what to do when you see a dot product, which is great. And if not, don't worry, I'm going to go over it from scratch, and it's really easy. So you're going to learn what a dot product is, and I want you to find the angle between a dot product. So this is going to be on quiz 1, okay? This other junk is going to be for the following week on quiz 2, so don't worry about it. So let's go over a quick summary of what you've learned so far. Not everything, because we learned, wait, just quick about when you add two vectors together, do you end up with a scalar or do you end up with a vector?
Vector.
Very good. The answer is vector. Good, good, good. What about scalar multiplication? Like, you know, when you take a scalar C and you multiply it by a vector V, like 2V, is your result a scalar or a vector?
It's a vector.
Excellent. Nope. No, you're right. Sorry. You're right. I'm not thinking. Yes, it is true. So, and why? Because you just distribute your scalar over the vector, you still have a vector. So what do we know so far? Everything we've been doing, you add two vectors together, you get a vector. You multiply a number with a vector, you get a vector. So what? What's the big deal? Well, this is going to be weird, what you're going to be looking at with the dot product. And it's like, oh man, because it's going to turn out it is some multiplying, but it's not scalar multiplication. You're doing something else, and so your answer isn't going to be a vector. It's going to be a scalar. So you're going to be doing another kind of multiply, and you're going to get a scalar. So before I go on, though, I want to just, and this is for those of you who are going to take linear algebra in your future, and you want to appear smart, there's another name for dot product. It's more of a high-level name. It's called the inner product. So if you're on the game show Who Wants to Be a Millionaire, you know, anytime soon, I just know that dot product is an inner product. It's a special kind of inner product. Okay, let's do both the two-dimensional and the three-dimensional versions of dot product. They're pretty much almost the same here. So, you know, if you have a two-dimensional vector with those components and another two-dimensional vector with these components, when you see a dot in between them, that means take the dot product. Surprise, surprise, surprise. That's why they call it the dot product. And then you're going to get a scalar, a pure number. And the way you get the scalar is you multiply the two x components together. You'll get some weird number. Plus, you multiply the two y components together. And then you add all that together and you're done. So how do you do it with 3D vectors? So it's what you think. You multiply the two x components together. Plus, you multiply the two y components together. Plus, you multiply the z components together, and then you get a pure number, and you're done. So now finish this sentence. The dot product is a
Scalar.
scalar. Good. All right, let's do some quick properties of the dot product. These are good to know. If you take a dot product, u dot v, it's actually the same result as v dot u. So good news, it doesn't matter what order you do your dot product. So you don't care. Now, for those of you who are like, great, be careful, because when I cover the cross product next week, order will matter, and so you're going to care. So be careful. If you need to take the dot product of a vector with the sum of two vectors, you can either do it like that. That's fine. In other words, do what's in parentheses first, then do the dot product. Or it is okay to distribute. That's totally legit. If you need to and it helps you, go ahead. Further, if you've got a scalar involved in the mix, you can either do it just like that, first do the dot product, then hit it with the scalar. Or if you prefer, do the scalar with the first guy and then dot product with the other guy. Or if you prefer to take the dot product of the first guy with the scalar multiple of the second guy. All three of these are equivalent, okay? I don't care which one you do, same deal. What if you take a dot product of any vector with the zero vector? What do you think you're going to get?
0.
Good. And now this one's weird, which is why I have two asterisks by it. When you take the dot product of a vector with himself, which is totally legal, it actually ends up being the same result as the magnitude squared. So I'm going to prove to you property 1. I know it's going to be, you're going to go, that's a dumb proof, but this is how mathematicians roll. If you take u dot v, you'll get this number, u1 v1 plus u2 v2 plus u3 v3. I can't write. If you take the opposite, so you want to do the v, that's a v right there. Come on, Surface Pro, work with me. You'll get v1 u1 plus v2 u2 plus v3 u3. But these are equal, and why are they equal? By properties of real numbers. Real numbers are commutative, and so it's totally illegal to say you have equality. So by the commutative property of real numbers. So that was easy. How about number 5? Is that really, really true? Sure it is. Let's look. Let's do the left-hand side. If you do v dotted with himself, you'll get v1 times v1 plus v2 times v2 plus v3 times v3. Okay, fine. Which looks like v1 getting squared plus v2 getting squared plus v3 getting squared. Okay, save that for later. What if somebody said, well, I want you to get the magnitude squared? Okay, no problem. We all know how to get a magnitude. It involves square roots. And then we're going to square that puppy. So when I get the magnitude, la, la, la. And you guys know from an algebra class, if you take the square of a square root, you just get the radicand. Okay, so I'm simplifying that. But then, aren't these two guys equal?
Yes.
Yes, they are. Done with the proof. Thank you. Okay, I got to move quickly now because I want to get to this idea of dot product used for something. So here are 3 two-dimensional vectors. We're going to keep it kind of easy, so we'll stay in the plane. Let's get u dot v. How do you do that? How do you start?
Well, you would multiply each of the components and then add them.
So I'm going to have 2 times 5, that's a 2, plus negative 2 times 8, and then what the heck is 10 plus negative 16 equal to? Quit.
-6.
You got it. And I'm done with letter A. I'm done. Now what about letter B? First you go u dot v, and then you multiply it with w. What the hell is that result going to be? Well, I claim we already did the crap that's inside parentheses. That's the dot product. So they're really asking me for -6 times w. That's scalar multiplication. And you already know about scalar multiplication. You take the -6 and you multiply it with the w vector by distributing the scalar. And so I'm going to get a vector here, positive 24 and negative 18. This is the answer for part B. And I'm done. So what about letter C? They want us to take the dot product of u with twice v. So they want me to take u dot product with twice the v vector. So what you need to do first is you need to honor the scalar multiplication first. So we don't do the dot product yet. I'll leave the dot there. I'm going to distribute the scalar of 2. So 2v is the vector 10, 16. Now I can take the dot product of these two guys. I'll have the product of their x components plus the, that's a -2 there, the product of the y components. And then that gives me what, 20 plus -32? And that adds up to -12. So final answer for part C is -12. For letter D, the magnitude of W squared, you're just going to take the sum of the squares of the components of W. So I'm going to go -4 squared plus 3 squared is equal to 16 plus 9. And that's going to give me a 25. And I'm done. Okay, it's scalar. Okay, I'm done with example 1. And now here's a good question. What the heck is the dot product good for? Oh my God. Here's the real answer. It says lots of things, but here's my answer to you. Take this class. Okay? So one of the nice applications, and by the way, this will be on your final exam question, and the midterm one. You better know this. I'm not letting you get out of my class alive without knowing this theorem. So here's the deal. If you have a vector v, or u, let's have it u, and then some other vector v pointing off in some other weird direction. And this could be in the plane or space. I don't care. It actually will also works in 4 dimensions, but that's another story. You'll do this in linear algebra, trust me. You want to find the angle between them. This is very different from what we did on Wednesday when we were working in 2 dimensions and we just wanted to find the angle theta that a 2-dimensional vector made with the positive x-axis. This is not the same angle. If you confuse these 2 formulas with each other and you think one is the same as the other, you're going to get burned. Pay attention. This is an angle between 2 different distinct vectors. The cosine of the angle can be found by taking the dot product of the 2 vectors and dividing by the product of their magnitudes. So in order to get the actual angle, you're going to have to do cos inverse of both sides in order to get theta, if somebody asks you for the theta. Okay? I'm going to need to skip this proof because I'm running out of time, but it's kind of cool actually. It uses the law of cosines from your trig class. So anyway, if you want to see it because you think it's cool too and you're really nerdy and you're a math major, come visit me in office hours. I'll be happy to show to you. Okay, moving on. What's another form of this theorem that I want you to also feel comfortable? It's the same darn theorem, but let's say I took this formula and I needed to clear fractions. What would you do to both sides of this formula if I said rewrite it without fractions? You'd multiply both sides by?
Magnitudes.
Magnitudes. So the other version, and sometimes when, well, which version do you use? Who cares and when do you use it? Well, version 1, this first version, I use when somebody gives me 2 lovely vectors and they want the angle between them. And I use this second version when they give me the angle between them and the magnitudes and they want me to find the dot product. Okay? So that's the deal. Now, before I actually do a couple problems with this, I want to get some, lay down some sort of basic ideas about this dot product and define what the heck orthogonal vectors means, because that is going to be on Monday's quiz. So first up, do you guys notice the right-hand side? Just take your eyeballs there and look at the right-hand side. Eyeballs there. Do you notice that magnitudes are always going to be positive? So when you multiply a positive with a positive, you get a
Positive.
positive. But cosine has lots of possibilities. Cosine can be positive, negative, or 0. So basically, it's the cosine that's going to make or break whether your dot product is going to be a positive or a negative or 0. So let me just draw some pictures here. If you have 2 vectors that are pointing in opposite directions, they're parallel, and the angle, if the angle between them is 180 degrees, which is the same as pi, cosine of 180 degrees is a negative number. What does this mean? It means your dot product of these 2 guys will definitely be a negative number, some negative. On the other hand, what if you had the 2 vectors have what's called an obtuse angle between them? So your angle theta is something greater than pi halves, but less than pi. Well, your cosine is going to be a negative number. So what does that mean for your overall dot product? It'll also be negative because it's the cosine that makes or breaks whether your dot product is positive, negative, or 0. Well, what if your 2 vectors exactly have a right angle there? So what if your theta is 90 degrees? Well, what is cos of 90 degrees? Quick.
0.
0. This means that your dot product will be 0. This is, I'm going to put a box around this. This is key. What if your vectors have an acute angle So you have an acute angle, not cute, but acute. So we're just basically saying that your angle lies between 0, oops, sorry, trying to write too fast. I hate it when I do that. 0 and 90, and here your cosine is going to be some positive number. What does this mean? It means your dot product will be something positive. And finally, the last type of possibility here is, what if u and v are pointing in the same direction? Well, they're obviously parallel. And obviously the theta, the angle between them, is 0 degrees, and cosine of 0 is 1, and that's a positive number. So your dot product will definitely be some positive number, okay? So I'm done with that. Now let's define the word orthogonal. Two vectors are orthogonal if their dot product is equal to 0. This is very key. This is going to be on quiz 1, midterm 1. It's actually going to be on quiz 2. Actually, it's going to be pretty much on every single quiz and final till the rest of the kingdom come. Okay? If you don't get this definition of orthogonal, you're in trouble. So in other words, cosine of the angle is 0, and your angle is pi halves, aka 90 degrees. Okay? So when you have orthogonality, you can also think of this as being perpendicular. Well, why don't you just say perpendicular, Professor? That's a good question, and I'll tell you why. We can visualize perpendicular if we're in 2 dimensions or 3 dimensions, because 2 vectors are making right angles with each other. But the word orthogonal also applies to 4 dimensions, 5 dimensions, 6 dimensions, 20 dimensions, and whatever, which you can never really say are perpendicular because you can't even visualize. Anything over 3 dimensions, you cannot graph. So this is about 8 years ago. I had this student in my class, and the whole semester you get saying, yeah, I know how to graph things in 4D, because there's such a thing as graphing in 4D. And I go, no, you can't, Renee. Put down the crack pipe. It can't happen. Okay, so let's do the last problem of the day, and then we're done, and then happy weekend. Okay? Or if you want, you can come see me in my office time today. Otherwise, I'll see you Monday morning. Here are some vectors, u, v, w, and r, and they give you the component form. All they want is for us to find the angles between each of these pairs of vectors, okay? And then for each pair, answer if they're orthogonal or if they're parallel or neither. Now, folks, orthogonal means 90-degree angle between them. Parallel, it means the angle between them is 0, so they're just pointing in the same direction, or 180 degrees, because if they're pointing in opposite directions, they're parallel also. Neither means any other angle that's not 90, 0, or 180, okay? U and V, what do you got here? Well, cos of the angle between them is the dot product, u and v, divided by the product of their magnitudes. So if I do the dot product first, 3 times -4 plus 0 times anything is just 0, plus 2 times 2, and then I'm going to divide that by the product of some square roots. This gets kind of ugly here. You know, you've got to go like 3 squared plus 1 squared plus 2 squared, and this is 4 squared plus 0 squared plus 2 squared. Oh my God. So what do we have here? We have -12 plus 4, which is -8, all over square root of 14. And this right here is what? Square root of 20. And remember, this is cosine of the angle. So your actual angle, and this is where you have to whip out your calculator, and I would be in degrees mode. Give me the degrees here. Let's see, I get, and I have the answers down here, but just I want to show you. It's 118.6, roughly. So is this the type of angle that's orthogonal? Yes or no?
No.
No. Is it parallel? Are these vectors parallel?
No.
Nope. Neither. So those guys are not orthogonal. They're not parallel. They got an angle of 118.6 degrees between them. Okay, fine. All right, let's do U and W. So if you're going for the angle here, it's going to be the dot product of U and W. This is the cosine of the angle, divided by the product of their magnitudes. So let's do the numerator first. This is going to be what? Let me change colors because we're getting kind of messy. U and W. So make sure you don't lose sight of who you're working with here. You're going to have 3 times 1 plus -1 times -1 plus 2 times -2. So I get 3 plus 1 minus 4. What does that equal?
0.
0.
Yeah, 0. I'm not even going to bother doing the denominator, people. Do I need to bother to do the denominator if the numerator is 0? I know the denominator will be something positive, you know, some positive numbers multiplied together. Here's what I know. Cosine of my angle is 0. So what's your angle? What's cosine
Zero.
versus 0? Not 0. Is your angle 0? No, your
No,
cosine of your angle is 0,
9.
which means the angle is
9.
parallel.
90 degrees. It's not parallel. You guys are falling asleep right now, I can tell. You're blowing this. Folks, these guys are orthogonal. Because we have a 90-degree angle. The dot product was 0. Go back to here. Check out the definition. If your dot product is 0, cosine is 0, which means the angle of that between them is pi half. Okay, and so V and R, very quickly here, cosine of the angle between the vectors V and R would be the dot product of V and R divided by the product of the magnitudes. So this would be, if I take the V and then 0 times 0. I hate this Microsoft Surface Pro. I'm just so sorry I bought it. What a waste of $1,500. Okay, divided by product of some square roots here. So I'm going to have 4 squared plus 0 squared plus 2 squared times 2 squared plus 0 squared plus 1 squared. Okay, so this is going to end up being, going pretty quick here, -10, and then this right here is what? Square root of 20, and this right here is square root of 5. Square root of 20 times square root of 5 is square root of 20 times 5, which I'm using some laws you may have learned in algebra, but that's square root of 10, which is 10. So this is really -10 over 10, which is -1. So I'm saying cos theta is equal to -1. So that means theta is equal to cos inverse of -1. Does anybody know what cos inverse of -1, or the angle who has a cosine of negative? You can use your calculator if it helps. Good. So now let's answer the question. Orthogonal, parallel, or neither?
Parallel.
Parallel. Okay, and I'm officially done. Woo, man, that killed me. You're probably dead too. Congratulations for making through today's dazzling lecture. I know it was a lot to take in, but we were running a little behind and I had to catch us up. We do not have the time this semester to even fall a little bit behind. It's a nightmare. Okay, I'm going to stay after a few more minutes for anybody who has any burning hair on fire questions. Otherwise, the rest of you, good luck on your quiz zeros this weekend as well as quiz 1. See you Monday. Bye.
Thank you. Bye.
Hey, Professor.
Yes.
Are you going to be posting this lecture right after?
Not right after. It'll be in the afternoon. I'll post the recording. The
Okay.
recording takes a while to render, Rick. Zoom takes a while to render. It doesn't like show up right away because Zoom does some cool things. It actually puts a transcript with it, and trying to understand and convert my weird talk into, which reminds me, I should probably stop the recording. And so it takes a while, and then once it's there, I'll put it up there for you this afternoon, I promise, okay?
Yeah, okay, because yeah, I have to go back on some of the stuff. It's just you went a little bit too fast, so.
I understand. You're also definitely welcome to come to my office hours today, Rick, between noon and 2.
Okay.
Come on
All right.
by.
All right, thank you very much.
You're welcome. See you then. Anybody else?
Hi, Professor Esky.
Yes. Bye?
Oh, Ms. Rasky?
Yes.
Rasky. What time is the Math 130 lab?
Same time, noon to 2.
Noon to 2?
Yeah, I'm going to do the virtual lab essentially the same time as my office hours. And
Okay.
the tutors, my power tutors are going to be there. I have 3 tutors to help out.
Right.
Janine, David, and Celso.
So it's the same Zoom link that I would click on to attend your classes, right?
No,
Different one?
no, my dear. I'm sorry. You have to go to the home page and you have to go to the Zoom office hour link. So please don't click on the class one, okay?
Right.
Because you're gonna end up you'll end up in Zoom. Zoom will go, your host is waiting, and you're gonna be sitting there all by yourself for hours. And then you're gonna get really pissed off at me. I've had students do that. And they're like, you weren't there at your office hours. And I'll go, I was there. Where were you? So Dominic, you can go to any one of I know you're in 2 of my classes, so it doesn't matter whose homepage you go to. I'll go to just 252, if you can see my screen. And you're gonna come down here and see where it says Zoom link for all office hours here?
Right, this is
You don't
similar-
need to register. This one, you don't have to register. This will take you immediately to your Zoom link.
Okay.
Does that make sense?
Yeah.
Yeah, don't use your class one. I will be there.
Okay.
That'll be a nightmare.
Well, thank you.
Yeah. Okay, any other quickie questions before I end the session?
Yes.
Thank you.
My question's for Math 130.
Okay, quick. Laser speed.
I just wanted to know how to actually submit it. I know you wanted me a text file, but did you literally want me to open like copy and paste it to the text file?
Yes.
Okay.
Exactly. You know, you can use like Notepad or WordPad. Notepad's probably the best because it doesn't change your fonts or mess with your font, which is
Okay,
going
so
to piss me
Notepad.
off because that means that when I try to copy and paste it into my IDE, I have to change some of the, like the double quotes get switched around into some weird ass character. But yeah, you're just going to copy and paste a text file, and then I'm going to copy and paste your code, and I'm going to run it.
Okay, that sounds good.
Have fun.
Thank you.
You're welcome. I'll see you guys later. I'm going to stop the share. I'll see you in my office hours. Bye.
Bye.
See ya.